Morning, folks. Please, you know what to do. Um, Today is going to be a very special lecture because it is one of the hardest ones, the more challenging ones. But there is a high payoff at the end, really high. The stakes are high. I would rather you keep your eyes on the board rather than keeping notes. Up to you, of course. Lecture is always recorded as usual. But I really want you to understand the gist of it. That's the most important thing for you and I today. It's going to be more tiring for me because it's you'll see what I mean in 5 minutes or 10. One thing I just noticed on my notes in an effort to better conceptualize Newton's law of motion for rigid spinning objects, sigma of torque equals inertia times moment of inertia times the angular acceleration. I gave you two examples. I gave you the example of a boiled versus raw egg, which hopefully you have found out that the boiled egg spins faster. And the reason is that the raw egg, the yolk, is fluid. So when you start spinning it, because of the forces, centrifugal forces, they're going to hit the rim, whatever, it's the shell distance where the shell is. Therefore, you have a non-uniformity versus the boiled egg, which is hard boiled, right? Which means the mass, the distribution of the mass towards the outer ring of the egg, the radius of the egg, if you will. That's why it spins faster. It has a higher moment of inertia. The same thing as the fidget spinner. The idea is identical, right? The fidget spinner with the metal balls at the end, right? Now here's a third example, which I think I was biking one day and I almost literally killed myself because I hit the brakes suddenly as if I was about to hit a wall or something, because in my head popped a silly question, not so silly, but in my head popped a question that, was like this. It was going like this. You guys bike, right? You see you have gears, bikes with gears. You see the discs, right? So when you're like in a straight line or even downhill, what gear do you have? High or low? You got low gear. Say 1 through 5. 5 is the high gear. Yes. High gear is 5, right? So high gear, what does it mean? You can control the pedal easier, right? So which disc is smaller? Gear number 5 or gear number 1? This is why I almost killed myself, because I, slammed the brakes and go like, I have to see which gear is which, and I have to, because I did make a hypothesis while I was biking, and I wanted to check the hypothesis right now. So I slammed the brakes, and I found out that the hypothesis was correct. So which disc goes with gear 5, smaller or bigger? I sense it's a 50-50. So high gear 5, you need to control the pedal easier, right? Even if you go fast, right? So what do you need? You need what? High torque. You need the pedal to be stiff. You need low torque, right? You guys with me? You need low torque. Therefore, the disc is small. Versus when you need a high torque going uphill, softer pedal. That's why the disc is bigger, because the application has a higher radius, higher torque. Yeah. Okay. That's what I wanted to mention. So this is by gears. Before we hit the more challenging parts of this, we need to do one example that also pertains to your homework. Not directly, but you'll see what I mean, and I will mention the relevancy of what we're going to find here. So the situation, you have a rod that it can spin about its center. The rod has a mass, a length, and moment, whatever, it doesn't matter. We know all that. And you have a bullet. You have a bullet that hits the rod at this angle that you see. The angle is also given. I'm going to define the angle with phi right there. and the bullet has a given mass and a given initial speed. You know the angle, you know whatever needs to be known about the rod. And the question is pretty obvious. The collision is plastic. The bullet sticks on the rod and they together start spinning. Now, depending if you have gravity or not, I want to find the omega right after the collision. You guys understand the question? Yes? Okay. Do we have a collision here? Obviously we do. Do we have internal forces? Of course we do. Collision means internal forces by definition. Can we argue that the angular momentum of the system is conserved because you have internal torques? Forces is torque, right? Forces acting on something that is spinning, it's torque. So internal torque, sigma of tau is 0, yes? So you can directly argue that the angular momentum of the system before and after the collision is conserved. Or if you will, do it. You guys following so far? Okay, so there's a problem here, though. We have a problem. What is the problem? What is the angular momentum of the system before the collision? Is there any angular momentum of the system before the collision? Of course there is. And this is why I wanted to bring it up. Because even for point masses like the bullets, moving with the linear speed, you can still define angular momentum. And the reason is very simple. I'll show you what I mean. So I'm going to call the angular momentum of the system, which is the bullet, essentially, equals to what? Moment of inertia times omega. Let's write omega naught, initial omega. We'll find out what this omega is. Now, the big question is, well, first of all, you know that point masses have moment of inertia, which is their mass times r squared. Yes, I think we sort of discussed this briefly. And the reason I'm bringing this up is the ladybox problem. By the way, you got an extension for the homework. You saw that, right? And the test is pushed back also. But now the question becomes, what the hell is R? What do you mean by radius? And I go like, okay, what if I were to sketch two axes like so? I'm extending my vector here, my u-naught velocity vector, yes? This still is angle phi, yeah? Now, right before it hits the rod, just right, it's a tad, it's femtosecond before. Can we say that my bullet, which has speed u-naught, right? Still has u-naught, but what about, can we calculate the omega naught for the bullets? Does my bullet have an angular speed right before it hits? And they go like, well, all I need to do is remind myself that, look, the linear speed is r cross omega, right? Remember when I said that this is a cross product? But cross products refer to what? Perpendicular vectors, right? Which means what? What is the perpendicular vector to rods and speed? Which component is that? This one. Yes? Which component? Don't answer that. The sine, yes. So in other words, your omega naught, which is going to be in vector form this, is going to be u naught sine divided, what is my radius? Look at it. If my length is L of the rod, what is the radius? L halves, right? You guys see that? So the big message here is that we can define angular momentum for something that is not moving in a circular pattern. All we need to do is define any arbitrary center of rotation like we have. That's the rod center and the radius. That's it. We good, guys? Very important. So yes, we can define angular momentum for something that is moving in a straight line. All we need to do is define a potential, center of rotation, and the radius. That's all. That is pertinent to some problem that you're going to see most likely in your homework of a kid running and jumping on a merry-go-round. Same thing, bullets sticking on hitting a rod, spinning rod. Yes. So that was the difficult part. The rest is really, really easy. So my L naught, the initial angular momentum is going to be the mass of the bullet, U, sine phi over L halves. Equation 1. Equation 2, what is the angular momentum of the system after the collision? Well, we know that this is defined as I omega, let's call this prime, after the collision, that is. And now, what is the moment of inertia of my system now? Let me write system here. What is the moment of inertia? It is the rod, yes, the rod about its center, plus what else? Now we have a point mass stuck to the end of the rod, yes? Parallel axis theorem says what? You just add this moment of inertia to the rod. Linear stuff, addition, easy, yes? So all you have to write is plus mass, L halves squared, and you're done. Equation 2. You set equation 1 equal to equation 2, and you solve for omega. Is it omega or, yes, omega. Or omega prime, I'm sorry. You guys with me? There is some algebra you can go about, but yes.
That first equation with the L squared on the top, so or L half squared on the top because of the
You're up. So, I did make this mistake, didn't I? MR. Oh, yes. So let me correct this, guys. I'm sorry. You're absolutely right. They mistake here. Thank you for that. The mistake is right here. So again, let me rehash this. So the initial moment is mass times R squared times omega, right? I screwed this up, guys. So please correct this. Yes. So what is it again? Mass times L halves squared, that is my radius, plus the omega naught, which is U naught sine phi over L halves. And of course, you can cancel this and that, and you're gonna have the mass U naught L sine phi over 2. Yes, that is the correction you need to make just for the L naught. It was a silly, thank you. I know whenever you raise your hand, there is something bad going on. Did you make this correction, guys? Do you understand what the mistake was? Yeah? We're good? Now the rest, I mean, I can show you what to put together. You're gonna have, this is the moment of inertia, the angular momentum before, sine phi over 2 equals to all this plus mass L squared 4 times omega prime. And then you solve for omega prime. And this is going to be that's it. Right? Put any numbers you want. Up to you. In fact, we don't have to restrict it for a rod. You can put any numbers for moment of inertia. Yes. Yes. No, the denominator has a 4 and the numerator has a 2. That's why over 2. Is that it? Yeah. Don't get me wrong, I'm very prone to mistakes, so you may be absolutely right, but I think I've quadruple checked that. So again, put in numbers you want, guys. This is the solution, right? Physics rests way before that. Now, get ready. I'm going to start this chapter with a multiple choice question. Number one, I have not opened the question yet. A marble is rolling. No skidding. I will explain what this is right now. On a very smooth surface with friction. A, will it stop? B, will it roll forever? It's A or B, and please disregard what the screenshot you got. So, I don't expect you to know the answer, but you see how many huge implications this question has. We're going to be talking about this today's lecture and Tuesday's lecture. It's a really fun topic, extremely fun, and sometimes it can be mind-blowing. So, and that's the way I see it anyway. I'll give you about 10 more seconds, 15 more seconds. Just go with your hunch. It's not, you don't have to know that. When you do have to know something, you can hear my voice. All right, everybody in. Polling now closed. 63% responded this, and the rest 37 responded this. Good. The next question is a marble. Oh, by the way, I forgot to mention what is skidding, but I will explain that to the full extent right now. Skidding means if it's partially rolling and moving, it's missing turns. That's what it means. Can you imagine that? Yeah. We'll see mathematically exactly what this entails. A marble is purely rolling on a smooth surface with friction, and then enters an icy one. A, will it keep rolling? Or B, will it start skidding or sliding, if you will, or sliding, skidding, the same thing. You get the point, right? Now, question it will be open now. All right, everybody in. And we have 14% responded A and 86% responded B. Look at these questions very closely, because as I said, there will be a few things that are mind-blowing, and the truth is that in both questions, the majority is wrong. You ready? Let the games begin. We're going to start with the following. Let me close this. First, we're going to start with what is pure rolling? What is the definition, the physical and the mathematical definition of pure rolling? And I'm going to show you a very nice image. It's not mine. I got it from a book. So we can really and deeply understand what pure rolling means, because right now we are transitioning from rotation, spinning, to rolling. Yes, different thing. So the definition of pure rolling is quite simple. For pure rolling, the center of mass of this object, say a disk, it has to move by S in a linear sense, and this S must be equal to the total angle, the revolutions that the disk makes, times its radius. Because if that is not the case, if S is not equal to R theta, then if it's skidding, meaning that the S will be greater than the revolution, the theta times the R. It has moved, if you will, more than it rotated. Yes. Does this make sense? At this level. We're gonna again rehash this many times. So immediately, if you guys remember the kinematics, your rotational kinematics, this directly implies that for pure rolling, we need to have this. And if we have this, we have to have this. So either relationship you choose, immediately it means that the other two hold true. The last one, of course, is the linear acceleration. And when we refer to linear acceleration, we are referring to the acceleration of the center of the mass, and that will be the angular acceleration. Are we clear on this? Take a minute. That is really important. We good? The first question that I'm going to ask you again is this. Here's a disk that we assume it has pure rolling. It doesn't skid. It complies with U equals omega r. It complies with linear acceleration equals angular r. And my question to you is this. What is the kinetic energy, in general terms, of this thing? And you go like, or you should ask, who's asking? Who is asking this question? Is an observer riding the disk located at the center of the disk, or is an observer just observing, stationary observers, looking at the disk rolling? Who is asking? Of course, as I hopefully have convinced you by now, the so-called frame of reference plays zero role. The answer must be identical, yes? No matter what axis or reference frame you choose, right? That is a really non-negotiable axiom in physics. Not just physics, but all science. So let us see with respect to the center of mass. That is right here, center of mass. So the observer at the center of mass sees two things. Sees the disk spinning about his location, right? But the observer also sees the disk moving forward, yes? Two motions combined, yes? So somebody would say that, well, my kinetic energy will be 1/2 mass, the linear speed. Again, when we talk about linear speed, we mentioned the center of mass, plus 1/2 the moment of inertia about the center of mass times omega squared. Are we clear on this? Are we? Let's put it together. Let's say that I it's a disk 1/2 mass r squared. So let's do the substitution. 1/2 plus 1/2 of 1/2 mass r squared. What am I going to do with omega? Given that I have, right, given that I have no slipping conditions, I have free rolling, what can I assert? That the center of mass squared divided by r. I can make this substitution, yes? We good, guys? If you put it all together, what you're going to find is this is equal to 3/4 mass linear speed squared. That is your total kinetic with respect to the center of the disk. That has Q rolling. Are we good? Yes.
Do we need to remember sort of what we need to remember the formulas for?
This is okay. Yes or no? You're gonna get used to them. Usually, I'm giving them to you. What I want you right now is to really engage on what we're doing. Do not worry about memorizing the moments. You're gonna use them so many times that, and even that, you got 3 things to remember: rod, sphere, and a disk. I mean, that's it. But typically, I'm giving them. Now, guys, what if I now ask you what is my kinetic energy of the same disk with the same Q rolling about the ground with respect to ground? Careful here. I'm going to ask you one question among other things. What is the speed of this point right here? Does this point have a speed? Yes. This point does not move, ladies and gentlemen. This point is a point of contact. It doesn't move. It stays the same. And you go like, what? So where did the energy go? If there is no linear energy, kinetic energy, where is the energy? And you go like, don't worry about it. I will prove to you that all the kinetic energy can be written as 1/2 I omega squared. But with what difference? Who's going to find this one? Can we have the same I as before? No. What I is this, folks? This I is with respect to, come on, give me something. The ground. How can we find the I with respect to the ground? Parallel axis theorem once more. So this is what? 1/2 parentheses. What is the disk about its center of mass? I'm going to write the parallel axis theorem now. 1/2 mass r squared plus mass times the distance squared, right? I hope you remember that. Excellent. Mass r squared. That is, again, my parallel axis theorem. Guys, if you do the same substitution here, because the omega is the same, the omega has not changed, which is U center of mass squared over R. Guess what you're gonna find? 3/4 mass U squared. The message here is very, very clear. It doesn't matter which frame of reference you're using. And I will prove this to you again and again. But at some point, I need to convince you that it doesn't matter one bit whether you select the center of mass as a frame of reference or the ground. The solution is always identical. We good so far? The next question is this. Imagine that you have a yo-yo, right? Here's the yo-yo. Let's assume it's a disc. And you're pulling the yo-yo with some force F. It is on a typical table where the friction is not zero. We'll see where friction, what friction does, because I can tell you from now, you don't really understand what friction is doing in these situations. You may think you know, but you don't really know. We're gonna flesh it out to the extent that it is way above and beyond the contents of your textbook, or the internet for that matter. The question is, what would happen if you were to pull the yo-yo really fast? Would it achieve pure rolling? Chances are no. It's gonna skid, yes? It will not roll. So to make it roll, what do you need? You need to go very, very, very smooth, right? Very slow, right? But how fast is fast, how slow is slow. Let's find the force that does it. Yeah? All right. Let us sketch the forces. And if you guys recall, when we're dealing with rigid objects, we typically apply Newton's law for point mass and Newton's law for rigid objects. If that rings a bell from the pulleys and the other examples that we have done, yes? So let's do that. Let's do the exact same thing. Here I have sigma of F equals ma. I am treating this as a point mass, and immediately I am referring to the center of mass. That's why we essentially boil everything down to a single point. Point mass is the center of mass of this disk. What are the forces acting? Force minus friction equals ma, yes or no? These are the two forces, yes? Equation 1. Equation 2. Sigma of torques equals I angular. What do we have here? Which force is producing a torque? And you go like, hold on, question? No, let me finish. You cannot have an answer. There is no answer right now. Again, the question is, which force is producing a torque? You guys have a question? Hold on, okay. Which force is producing a torque? There is no answer to that. The question is by itself ambiguous. Why? If I want to answer and find which force is producing torque, I need to find the axis of rotation. Otherwise, I cannot define which force is acting and producing a torque, yes? So what is my axis of rotation? Well, you pick your two. I mean, you have options. Option is the center of mass, yeah? And another option is the ground, yes? So I'm gonna choose the ground because I feel like it. And I will prove to you again that it doesn't matter which one you choose. We use so far. Now, in light of this, which force is producing a torque on the disk? No, it's not the friction. Of course not. Because the friction goes through the point of rotation. We said with respect to the ground, right? Guys, I know in advanced or AP, whatever, they teach you just one thing, the friction is doing everything. I know that. That's where you come from, right? But this is where the things go south, because they teach you just one thing, not the other thing. And they have you memorize, oh, the friction is doing everything. That's wrong, dead wrong. I know what the AP curriculum entails, and it's just, anyway. Again, the question is, which force is producing a torque with respect to the ground? You don't have any other option, say it. It's a force. So what is friction doing? Well, at this point, nothing. Let's write it. What is my torque? Force times R equals to moment of inertia. Careful here. What is the moment of inertia? Is the moment of inertia about the center of the disk or about the ground? We just did this 2 minutes ago. Say it. About the ground. That's right. Let's write it. Which is what? 1/2 parallel axis theorem plus mass R squared. Now, folks, if I assume that this force that I'm applying does not produce skidding, but it does produce rolling, can I sub the angular acceleration with the linear acceleration over the radius? Can I do that? That is legit. That is the assumption, not just the assumption, that is the statement, the axiom when you have pure rolling. So this is going to be linear acceleration over R. Yes or no? You do the algebra and you find out that the R's cancel out and you end up with force equals to 1/2 force equals to 3/2 mass times acceleration. Equation 2. Everything else canceled. I mean, the R's cancel out. We good? Excellent. Now let me combine out of curiosity these two equations. And I'm going to sub, obviously, equation 2 into equation 1. What do I get? 3/2 mass acceleration minus friction equals to ma. Yes or no? Which means that friction is 1/2 mass acceleration, or 2 times friction equals mass A. Equation 3. Yes or no? Then I'm going to take again equation 3 and put it back in equation 1. Sigma of F equals ma. And what do I have? I got force minus friction equals, instead of ma, now I have 2 friction, which means force must be equal to 3 times the friction. Or you can say that, of course, force is just mu 3 times mu mg. What did we find here? We found the maximum force you can pull your yo-yo so that it does not slip. Given, of course, given the coefficient of friction that you have. I'm going to repeat this again. We just found, and I will explain why I called it the maximum. We just found the maximum force the yo-yo must have for pure rolling. Why do I call this the maximum? Do you see any inequality here? You don't see, you see equalities all along, right? But think about this. Why am I calling it the max? Because I will prove to you very quickly that if this force was greater than 3 mu mg, we wouldn't have rolling. You know how easy this is? Well, if we assume that we have skidding, that would mean that the linear acceleration would be greater than the angular acceleration times r. Not equal, which is rolling, it will be moving faster than it's rolling, or it will be accelerating faster than its angular acceleration. Yes, which would mean that immediately the angular acceleration would be less than a over r. Yes? And now do me a favor and take this inequality now and go back and put it there. See what I'm saying? Thereon, you will not be solving equation, you'll be solving inequality. And if you substitute this over there, you're going to end up that, you know what, my force must be greater than 3 times mu mg. This is why I called it maximum force. If it is less than that, it's all good, because you will still have rolling, but you will not have rolling when A is greater than the angular acceleration over R. You guys with me? Take a minute to discuss it.
Those multiple choice problems you gave us at the beginning, I was part of. I mean, I sounds like I got them both wrong because I was in the Jordan, but part of what I was thinking about those was like if there's rolling, there's friction, and there's heat, and it's got to eventually dissipate and stuff.
You know how intricate this answer is, but we're gonna flesh it out. I promise you. I will dedicate half of a lecture, next lecture, to address this question. Do you feel that I'm pulling you out of your comfort zone from the high school AP physics? If the answer is yes, my response is good. Because what the way they have taught you physics in the so-called AP is completely false. It is, here's the formula, here's the problem, that's not physics, that's not science. Science is using this, and if you're not using this, you just lead to you're led to memorization, and that's physics or science either. So if you feel that you're pulled out of your comfort zone, that is exactly my goal. Because this is what you learn. So please leave all the baggage from AP behind. Okay? Excellent. It's gonna pay off, I promise. Are we good so far? Now it's time for me to prove to you that if I pull you back to your comfort zone, and yes, friction does the torque, the answer is identical. Shall we see that? Let's do it faster this time. So here's the ball, the disc. Here's the force. Here's the friction. And my frame of reference right now is the center of mass. Big deal. What do we have? What do we have? Sigma of F equals ma. Point mass, same forces, nothing changes. We good? As far as a point mass, it doesn't care if it's a center of mass or a rotation about the ground because guess what? The point mass does not do any of that. Equation 1. Equation 2, sigma of torques equals I angular about the center, which force is producing the force, the torque. You said it. Come on. Friction, yes. Friction times the radius equals to moment of inertia. What moment of inertia will you choose? The center of mass, because that is our point of reference. Yes. Which is what? 1/2 mass r squared times the angular acceleration. And I'm going to do the same thing. Since we have pure rolling, or we see pure rolling, I'm going to substitute this with angular acceleration divided by r. Same old, same old. And solving for that, you're going to find that friction is 1/2 mass times acceleration. And guess what you do next? You take this, you put it back there, and what do you find? You find that, well, this again means that 2 friction equals ma, and you take this and put it back there, and you get that the force must be equal to 3 friction, or 3 nu mg. Did I convince you now? Even better, that it doesn't matter one bit which reference you choose. Good. Next question is inclined plane. You have the same disk. You have a nu, and the question is, what will be the minimum friction coefficient that I need? The minimum friction coefficient that I need. So this disk goes down the plane with no skidding. Yes, it's the same question as before. Identical. Yeah. I'm going to choose, because I prefer this, the ground again. And you will see why I prefer the ground a bit later. I'm going to sketch the forces, typical axes for an inclined plane. Here's my weight, and this is my friction. I am going to do the exact same thing that I did a minute ago. I'm going to write sigma of F equals ma. Sigma of F equals ma. And sigma of torques equals I angular. Same method. Sigma of F equals ma yields the following. What are the forces acting on this disk from when this is treated as a point mass? Well, we know what to do. Free body diagram. This is going to be my mg sine, if this is phi, of course. And this is my f, the mg, what am I doing? Yes, mg cosine. And this is a normal. Yes. And friction, of course, goes also along the x. That is pretty trivial. Let's write that. Mg sine minus the friction, which is mu mg cosine phi. I hope we have established this. We don't no longer need to flesh it out, right? I hope you realize this, equals ma. And that is my equation number 1. Yes? I mean, yes, you can, before we write this as equation 1, you can cancel out the masses as typically, and you get g sine phi minus mu g cosine phi equals a. Okay, big deal. We knew that for a point mass, this is the acceleration. Yes, that is equation 1. Equation 2, sigma of the torques equals IA. What force is producing the torque? Again, now we have defined the reference. What force is producing the torque? The weights. Which components? The sine, the x component, yes? Of course. So you get mg sine phi times r equals to moment of inertia. Careful here again about what? The grounds. We know this. How much is it? 1/2 plus 1 is 3/2 mass r squared times. What are we going to do? Again, because we seek pure rolling angular acceleration, we sub it with what? A over r, yes or no? You go about this and you find that the linear acceleration, I'm sorry, it is 2/3 g sine phi. Guys, take a look at this. This is a profound finding. Take a look at this. Take a really good look at this and tell me what's wrong with this picture. We're dealing with an inclined plane with friction. And I'm telling you that, you know what, acceleration has nothing to do with friction. Aha, what a finding. That's what I'm telling you. Yes? Look at this. Isn't this true? Unless we made a mistake, and we didn't. I didn't. I'm taking the responsibility here. Just want to distribute when we are making something a mistake. It's not I make it. Look at it. Take a minute to breathe it in. It tells you right in your face that I don't care what your mu is. Isn't this surprising? It is. So let me finish and I'll go back to, because again, the question was find mu, yes? Find the coefficient that can do that, the friction coefficient that can do that. Again, an oxymoron. You go like, why do I need to find the friction? Because the acceleration has nothing to do with the friction. You see the conundrum here? Do you see the conundrum here? But algebraically, I can find it and go like, how? Well, you're gonna take this acceleration right here. Let's call it what, equation? Do we have numbering? No, that's okay. Go back to the sigma of f equals ma that you have from before. Where is it? Oh, here it is. I'm sorry. It's right here. Yes, you go equation 1, and you have g sine phi minus mu g cosine phi. I'm making a substitution with 3/2 g sine phi, and you come up with mu equals 1/3 of the tangent. And you go like, are you kidding me, man? From one side, you're telling me that acceleration of the disk down an inclined plane has nothing to do with the friction. On the other hand, you tell me that we need that friction coefficient. You know how easy it is to solve this conundrum? Do you understand the contrast here? Do you understand the oxymoron here? What is the answer? The answer is very simple. Folks, what did we say in the very, very first place? What did we assume? What was the assumption? What was the only assumption that we made? That is the only assumption we made. No other assumption was made, yes? That we have pure rolling, yes? And yes, the answer is friction has nothing to do as far as we already have pure rolling. Friction has no business when something is already rolling. Friction has zero business if something is already rolling. Once more, friction has no business if something has already attained pure rolling. Does this sink in? Now, but in order to have pure rolling, in order to stay pure rolling, we need this friction coefficient. You guys with me? But now, the way we're approaching things, let me ask you this. A marble is rolling, purely rolling, on a smooth surface with friction. Answer A, will it stop? Or answer B, will it continue forever? Raise your hand who votes for A. Oh, come on. I just said that friction does nothing. What did I say? It's rolling. There's a mistake, I think. Say what? Oh, okay. I'm sorry. Yeah, right. I put it to a vote. New votes. You can reduce yourself if you like. New votes. Is it going to be A? I don't want to see any hands at this point. Or B? Yes. So what you're telling me right now is that if I toss a marble, it's going to keep going. It's going to reach Calhoun.
Perfect world.
Okay, so what makes it unperfect?
Imperfections in the ground and imperfections.
Precisely. It is not friction that stops a marble rolling, folks. It is not friction. It is, as our classmate said, imperfections on the ground. And I'm going to show you a very illuminating plot. It's not mine, because usually my plots, you know how they look like. It is these imperfections. Give it a second. Hopefully it's going to paste. Yes. It is these imperfections that produce a torque, a counter torque, if you will. This is what's stopping the marble, not friction. Again, as long as it has achieved pure flow. You see the normal forces that no longer go through the center. You have normal forces that sum up to, well, something to the right here, say. That is the sigma of normal forces, if you will, which is a tad to the right of the center. Guess what? That's a torque. That is what? Countering the torque that you already have. Not torque, the rotation. Now let me ask you something again, the second question. A marble is spinning on a rough surface with friction and enters an icy surface. A, will it keep rolling as nothing happened? Or B, will it start skidding? Who votes for A? Will it keep rolling? That's the right answer. Why? I just told you friction has nothing to do as long as you have rolling. How does this for AP Physics? Now let's do a fun experiment. Did I have it? I do. Oops. Inclined plane. And on top you have a sphere. You got a hook. What else is there? A cylinder, I think. A disc. You have identical masses. less u, plus radii. So I want you to imagine that at the top of an inclined plane, you have a sphere, you have a hoop, which is like a cylinder, if you will, and you have a disk. Yeah. And you let them roll from the exact same height. You have ensured that if there is pure rolling going on, which one will hit the bottom first? The sphere, the disk, or the cylinder? The empty, the hollow cylinder. While you're thinking, let me prepare the demo. Low. And here it is. The hoop has, I think, one. The coefficient is 1. The disk is 1/2 and the sphere is 2/5. What does your hands tell you? Just intuition-wise. What do you think? If you just try to imagine, what do you think is going to win? Yeah, intuition. What do you think? Yes. The hoop. Anybody else? I'm not asking why. I'm not asking. Well, okay. Let's ask you why. All right. Let's. The spot is on you right now. It's on you. Because I like it. It's a valid answer at this point. Both mass and radius. Okay. 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 You are close to the answer, like by 180 degrees. You just said the exact opposite. Oh no, that's okay though. No, that's it's a very good answer. But you got it flipped. You got it backwards.
Oh, wait, this has to be the center of hybridization. Oh, so I want to know the, not the sphere, but the other one. That's like, that's, yeah.
Ready? The sphere always wins. The sphere will always win, of course, as long as we're comparing apples to apples, the same mass. You can see that the radii are the same, and we trust that the masses are also the same. But yes, I've tried it too. The sphere will always be a winner. I'll give you 5 minutes to prove it. Prove it. So I can also take a break. 5. This is a half, and the loop is 1. Yeah. All right. We're gonna make a really quick proof. Just half a line. You ready? Where are your 100 golden coins? Yet again, these 100 golden coins, where are they? MTH, right? They all start from here. So this is H. Typically, you measure it from the center of mass because this is going to come down here. So the delta H is center of mass to ground. Okay. Can I write MGH at 0.1 will turn into what? Well, you go like, do you want me to write about the center of mass or about the center of about the ground? It's the same thing. If you write it about the center of mass, you're gonna write down here, it's gonna have 1/2 mass u squared plus 1/2 I center of mass omega squared. That's with respect to center of mass. And if you write it for the ground, it's gonna be just 1/2 I prime omega squared. Are we clear? We saw that multiple times. Yes? So it doesn't matter which one you choose. I'm going to take this because it's shorter. MGH equals to 1/2. I'm going to write I with respect to ground. They all objects will add mass r squared. Right? All objects will add mass r squared because the center of mass, the distance is r, the same radii, as we said. The same mass, golden. So I'm going to write, instead of moment of inertia, I'm going to write C mass r squared omega squared. C is a coefficient. That's all it changes between the objects, yes? The coefficient. And I'm going to substitute again omega with u squared over r squared. We have rolling. And then you're going to end up with r squares go home. Masses, of course, go home across. And you're going to end up with what? You're going to end up that the speeds is going to be the square roots of 2gh over c. And we are done. The higher the c, the lower the bottom speeds. Yes? Which one has higher c? 1. The other is 1/2, and the sphere will always win. End of story. Cool. We will not complete this problem. But instead, I will upload a simulation which you will work on for Thursday, for next Tuesday, this coming Tuesday. You will work on Symfy and you will try to solve the problem because, folks, this is paramount because you're gonna finally understand what friction is doing in these situations. We know that friction doesn't do anything when pure rolling has been achieved. Nothing, it's out of the picture. But what if you guys watch Simpsons? So and so, it's better than a no. Who's a no? Okay. Should be a crime. A felony if you say no. What is the favorite sport to play? Oh. Do not watch it. So what? Soccer. Bowling, of course it's bowling. Thank you. Who said it? Of course it's bowling. You're just faking it, man. You're just.
There is a soccer Simpsons name in about every single arcade, so.
That's a fella.
Hey, are you dressed like Bart?
Bart? No, it's not. Bart has a red t-shirt with blue shorts. You're not watching Simpsons either, right? Shame on you. All right, so if you have you been to a bowling alley? What an exciting sport. Yay. It is like, what do you call this? What do you call this? Baseball, right? I mean, come on, you have NBA and, right? That's a sport, man. It's an outdoor activity. Baseball is an outdoor activity, man. It's like, anyway, that's my personal take anyway, so. I was brought up with soccer, So here's a bowling ball that you toss on the alley, and what does the bowling ball do? Well, no, if you see close up, it starts rolling at some point down the alley. It doesn't start rolling from the get-go. No. There you go. It skids. Okay. So we give the bowling ball some initial speed. You nod. The coefficient is pretty low. That's why it's called a bowling alley, and you're not supposed to walk on it because it's very polished. The friction is very low. That's why they do it. And at some point, you have some skidding going on. The only thing that you know is that your initial speed, U naught, is 5 meters per second. Your mu is 0.05. This is a disc. I'm sorry, bowling ball, a sphere. Do I have it as a sphere or as a disc? No, a sphere, of course. I'll be really dumb. A sphere. And the question is how many pins it will hit. I'm just kidding. No, that's the question is find the distance where you are going to have pure rolling. And for that, I am going to add, so find the distance. And second, find out what friction does. And this will be the revelation. That will put the last nail on the coffin of this challenge. I'll see you next week. Like 5, yeah. It has none of that. It's you just throw the ball at 5 meters per second. That's it. The what pattern? Friction is 0.05. Yeah. Yeah, constant. Yeah. Oh, I guess that they. Oh.
Yeah, so it has less friction at the start than it is in the second half. It has more
Let's do the problem with Bahrain friction then.